We begin our measurement lab by preparing some wires to use as test points. Next, we solder these wires to various points on the Raspberry Pi traffic light. To measure the resistance of the actual components on the traffic light board, we'll measure at these test points. Solid green, blue, and orange, and green, blue, and orange white stripe. Those test points will measure directly across the three resistors. So we're looking for 100, 100, and 330. We've got our ohm meter set to ohms. We're in auto ranging mode, so we'll just go ahead and take our readings. So across the blue pair, we get 329 ohms. Across the orange pair, we get 100.1 ohms, and across the green pair we get the 100.1 ohms. So the components and the schematic match. Then we'll mount the traffic light to the Raspberry Pi GPIO, paying attention to the pin order. We attach the switch between pin 25 and ground. The traffic light is on the inside head row, with the green light being attached to pin 11, the red to pin 9, and the yellow to pin 10. Now our traffic light is mounted, and we are ready to begin our test. These pair are across these resistors right here. So the test points on each pair, the white stripe is closer to the LED. The white stripe is here. The solid blue, orange, and green this is the green, this is the orange, and this is the blue. And respectively, this is the red LED, the yellow LED, and the green LED. So red, yellow, green. And there's our GPIO pins. Ground is pin 1, and this is green, red, yellow. We've booted up the Pi now, and we're running the button press program. Before we light the first button, let's go ahead and make our connections. We're going to test the voltage drop across this red LED. Reading 0 voltage. We'll turn the LED on. The LED is on. We're reading 1.88 volts. We're going to throw the 4 away because all the accuracy we need is 2 decimal points for what we're doing. So 1.88 volts dropping across the LED. Now if we move this measurement point to here and here, we're now measuring the voltage drop across the resistor, and it's 1.27 volts. Okay, so let's remember those, 1.27 and 1.88. Now let's read our the voltage, our supply voltage. And our supply voltage is will be the same as this blue wire right here. So our supply voltage is 3.16, 3.15, 3.16 volts. So we're going to say 3.55, 3.15. Uh, and if we look at our supply rail, we see we're a solid 3.3, 3.29 volts. So we're dropping, let's turn that off. We're dropping some voltage in the junction that pulls that pin down. And that's, we'll do the calculations, but you could see that from our previous calculations that we're overloading the pi, or the pi GPIO. Okay, we've looked at the red, and we note that looking at the diagram, the red is by as current limiting resistor at 330 ohms, and we see that green only has a current limiting resistor of 100 ohms. So obviously we're dropping less voltage across this resistor and more voltage across the green LED, and that goes along with what you've learned, that the higher the frequency of light, green being a higher frequency than red, the greater the forward voltage has to be for the LED to switch on. So now performing the same test on the green LED, we note that our voltage drop across the LED is 2.808 volts. 2.08 volts, which is greater than the red LED voltage drop. And now checking the voltage drop across the 100 ohm resistor, we see that we have a voltage drop of 0.88. And finally, again, looking at the supply voltage, you see our supply voltage is down to 2.97. We are seriously overloading our GPIO with that green. So we see that our traffic light LED designed for the Raspberry Pi is actually overloads the Raspberry Pi GPIO. So how do we solve this? Because we want to continue down this path in programming, and the way we can solve this is by adding an additional board. Now, this IT Arduino Leonardo, which is a Arduino Leonardo knockoff. This is where we want to go. But until we go there, let's take a look at what we've seen in this lab demonstration. Okay, we see that the red LED, we tested the red LED and the green LED, and we see that the red LED resistor was within 1 ohm of its advertised rating. Uh, the resistor voltage drop was 1.27 volts. The diode forward voltage drop was 1.88 volts. Added together by Kirchhoff's law, we find that that's 3.15 volts, which is the same as the measured voltage, supply voltage. Um, Solving for I for amperage, how much amperage is the circuit pulling? We have a 1.27 volt drop across the resistor at 329 ohms. That's 4 thousandths of an amp or 4 milliamps. Flag that. We calculate the power on that. It's volts times amps, so 1.27 volts times 4 milliamps equals 5 milliwatts of power uh, being consumed. So that is more than our maximum load on an RPI 3.3 volt TTL GPIO pin. That load is 3 milliamps, and so we're a milliamp over that. On the green LED, we measured that resistor at 101 ohms within specifications. The voltage drop across that resistor was 0.88 volts. The diode forward voltage drop was 2.08 volts. Uh, those, according to Kirchhoff's law, should add to equal the supply voltage, and they do. Uh, 2.96 is what we read. Um, you could see this obviously loading that supply down considerably. 3.3 volts is what we'd expect to find on that pin, and it's being pulled down, loaded down to 2.96 volts. If we do the, if we solve for amperage, um, I equals 0.88 volts divided by 101 ohms, so I equals 9 milliamps. The power equation on that would be 0.88 volts times 9 milliamps for a power consumption of 8 milliwatts, considerably more than almost twice the wattage of the um, red LED. Here we go. The green LED consumes more power than the red LED. This is because the green LED carries more energy because of its higher frequency. The 3.3 volt TTL levels on the RPI Raspberry Pi GPIO are logic level power. They're meant to drive other logic gates or power amplifiers such as FET switches. The ITE Arduino Leonardo and Arduino Leonardo clone is a microcontroller which can deliver much more GPIO power than the Raspberry Pi microcomputer. So that concludes the lab for interfacing electronics. Thank you for your time.